Hello, my name's Chrissy. This is the screencast for exam one for kinetics. So starting off with 1A, the batch reactor. I started off by using the mole balance for the batch reactor, which is pretty much just the rate of change of moles of A equals to the negative of the reaction rate times the volume. And then since the rate law is R equals KCA squared, which is the first section right there. And the reactor volume is constant. I substituted Ca equals Na over V. This gave me an equation that I could integrate to relate time in initial moles and moles remaining. And then after integrating, I rearranged to solve for the rate constant K. Then I plugged in the given numbers for volume, time, and conversion to calculate K in units of meters cubed per moles times seconds. This shows how the rate constant connects to how fast A reacts in a batch reactor. And then for part B, it's just the explanation. And then for part C, the CSTR flow rate. For the CSTR, I use the steady state mole balance that says what goes in must come out, must be equal to what comes out. I expressed the alloy concentration in terms of conversion and then subtracted the same rate law as before, which is just the R equals, as you can see above. And then after simplifying, I solved for the volumetric flow rate using the known values for K and then Ca naught, conversion and reactor volume. I calculated V in meters cubed per second. This flow rate, this shows the flow rate needed so that the reactor reaches the same conversion as in the batch reactor case. And then moving down to the PFR flow rate, I used the differential form of the mole balance, which relates to the change in conversion to reactor volume and the flow rate. Then again, substituting the rate law and express the concentration in terms of conversion. And then I integrated over the conversion range from 0 to 0.48. After solving the integral, I rearranged using the known reactor volume, K, and then the feed concentration. This method shows how the flow rate and reactor type affect conversion, since PFR usually achieves higher conversion for the same reactor size than a CSTR, which is explained in 1E down below. Moving on to question 2. Skipping over part A, but again, for part A, the book values are on top and then the values that were found are on the bottom. And then for part B, to find the equilibrium conversion for the reaction between diethylbenzene and benzene forming ethylbenzene, I first wrote the balanced equation and expressed the change in each species in terms of the reaction extent. Then I used the thermodynamic data above to calculate the standard Gibbs free energy change at 400 degrees Celsius. From that, I determined the equilibrium constant. And then I related that to the partial pressures of each species using the equilibrium expression, as you can see here. And then I used stoichiometry and I substituted the mole fraction in terms of the extent of the reaction in total pressure, and then solved for the equilibrium extent, which gave me the conversion. And then this process showed how the thermodynamic properties connect to the compositions under certain temperatures. And then for part C here, I applied the Le Chatelier's principle and the sign of delta H because this reaction increases the number of gas moles, lowering the pressure, which shifts the equilibrium towards more products while increasing pressure favors the reactants. Similarly, since the reaction is an endothermic reaction, higher temperature drives equilibrium towards more EB formation, while lower temperatures favor DEB in benzene. These are supported by the given X values that were then found at 300 and again at 600. And again, this was an endothermic reaction, and each one was solved just like part B, just for different temperatures. And then moving along, we have question 3, part A. And in this case, we started off by just writing everything we were given, and then we had the reaction where the rate depends on both the Ca and the Cp. So then I set up the mole balances for both reactor types. For the PFR, sorry, for the PFR, I started off here. And express concentrations in terms of conversion and stoichiometry of the reaction because this is an autocatalytic reaction. The rate increases as more product forms. I then did it numerically and using polymath. However, I did do it numerically starting off, and then I used polymath to double check everything. And then I just integrated here when I did it numerically, put a over 1 minus x plus b over 0.1 plus 16x, and then I just put those equal to 0, found what a, found what b was, then I did the integral of that, and then I did VPFR, and then that equals, and then I just plugged everything in for the equation, substituted, and then I got 6.697 meters cubed. Moving down to the CSTR, which is a lot simpler. I already had all the known values. I mostly just had to find the new CA, which was just CA minus 1 minus 0.8, which is 1.6. And then the CP, which is 12.9. I plugged those values in, got that to be 5.168 meters cubed. Moving past part B, which was just the explaining, we move on to part C. For the recycle problem, I started off by defining the recycle ratio. In this case, half the reactor outlet stream is returned to the feed. That was given in the problem. That means that the inlet concentration are a mix of fresh feed and recycled product. To find the new conversion in the final outlet, I wrote a mole balance that included the recycle stream. Um, and I also wrote it two different ways. You could just do x equals xr over 1 plus r and then 1 minus xr for the recycle stream. And then where xr is a conversion inside the reactor and r is a recycle ratio, using the relationship, I could calculate the overall conversion based on how much product is being recycled. And then that was, and then using all of that, I just got the equation for the multiple different ways you could find the inlet, and then the volume. And then for the extra credit using polymath, I just approached it in the same way, and then I used polymath to directly by modifying the original PFR equation to include the recycle flow, and then the problem solved for the concentration profiles and gave the new overall conversion. This approach worked in order to find the XP, which was asked for when solving.